Alright, today we're going to go over iteration, which is it's different than what we've been doing previously with recursion. Let's take a look at what we have been doing. So this is the factorial function that we've done before. Fact of n equals 9 and n times the fact of n minus 1. Alright, now this is I believe this is called natural recursion, and the problem with this is that the computer has to remember that you multiplied something by n, because it doesn't know what the value of this is quite yet, so it must first find out this before it can do anything with this times n. So what you end up getting is, like, for factorial 5 you get times 5 times 4 times 3 times 2 times 1 times 1. And so the computer builds up this whole thing in its memory before it can actually calculate anything, before it can do the arithmetic. Now this is fine if you're just doing, like 5, but what if you were doing 10,000? Then your computer might not have enough memory for it, and it would crash or something like that. Let's see, another example of this is, for instance, when we're constructing lists, like append, where we append two lists together. We do this basically. Append to we'll just name this append like that. Alright, so you append ls1 and ls2. So we do a cons car of ls1 onto the append of the coulter of ls2. Coulter of ls1. No, not the coulter of ls2. Alright, so you append ls1 onto the coulter of ls2. Alright, so obviously it doesn't know this yet because it has to calculate that. So what you end up getting is, a bunch of cons statements, sort of like the multiplication statements here. And that builds up in memory as well. Alright, so is there a way around this? Well, we've already done some functions that are recursive, but do not build up the memory like this. For instance, the member function. Do you remember that member, the predicate, item and ls, and it searches through ls to find item, and if it doesn't find item in the car of ls, then it just does member of item in the coulter of ls. And it just cycles through the list, and it basically passes on a reduced list to the next call of member. And this is called a Taylor recursive function, and these are also iterative. Okay, so luckily we can actually convert a lot of these just regular naturally recursive functions into Taylor recursive functions. So that's what we're going to do with the factorial function here. Okay, so let's define it like the old way. Define fact lambda n times, if equals n 0, then 1, otherwise multiply n times fact of minus n1. Alright, I'll just run this. Actually, I'll run it in petite scheme. Let's see. Oops. Alright, trace fact. Then we'll do fact of 5. See, we have to keep calling it This, because it's indented, that means that fact 5 has to wait for fact 4 to complete before it can calculate what fact 5 is, and so on. So fact 5 is waiting for fact 4, which is waiting for fact 3, which is waiting for fact 2, fact 1, fact 0, and it's all building things up. Now we're going to do an iterative fact. Call it fact it. Fact it. Okay, lambda. Now the trick of this is called also the accumulator method, where we instead of adding up the value or multiplying up the value at the end, we include an accumulator on the side of the function as a second argument. So we'll just say n and accumulator. So if equals n 0, then we're actually, instead of returning 1, we're going to return the accumulator. And otherwise, we're going to run just fact it again. You can tell it's going to be it. If it's naturally recursive, then we'll do something like multiply or cons or divide or subtract or add. But since this is just iterative, we're simply going to yes, we're just calling the function by itself again. And now what will we change in this? We're going to change the accumulator. So we'll fact it of minus n1, and then for the accumulator we shall multiply n times the accumulator. Okay, now but what do you start out when you're starting the accumulator? You actually would start it out with 1. So I'll change this and have it call fact it, so the user doesn't need to know how to start the accumulator. Fact it of n and 1. Okay, now we'll run this and see if it works. Oh, yes, I have to define it. Alright, then fact 5, which I believe equals 120. Yes, 120. Alright, now let's paste these in Ches scheme and I'll show you. Oops. Trace fact it. Alright, now run fact of 5. Now you see how flat this is. That means it doesn't have to, each one of these is taking up its own memory, but then it gets replaced by the next bit of memory. So the whole thing takes a constant amount of memory. Alright, so fact it of 5, 4, 3, 2, 1, 0, etc. Alright, now let me go back and explain why we start out with the value as 1 for the accumulator. Let's think of the base case. If n equaled 0, then we'd want to return an accumulator of we're returning the accumulator here when n does equal 0. So if we called fact of 0, which is mathematically defined as 1, then this would return 1 because the accumulator would be equal to 1. And if we called fact of 1, it would be 1 as well. Now it starts out multiplying n right away by the accumulator, which is 1. So basically, instead of having the normal, let's say 5 factorial the other way, it'd be times 5 times 4 times 3 ... But this way it's like times 5 and 1, and then once that gets done, that will equal the accumulator of 5, and then you multiply that times 4, and then you multiply that times 3, and then you multiply that times 2, and you get your answer in the accumulator.